Hello everybody and welcome back. Welcome back. We're looking at question number 9 on the 2018 Manitoba Mathematics Competition. And what have we got here? If P and Q are consecutive, now they're bothering to underline consecutive, so I'm going to especially note that. Consecutive prime numbers, both greater than 3, so that's an important thing to know about. Prove that P plus Q has at least 6 different distinct positive divisors. Now, I don't think this 6 has anything to do with the fact that greater than 3 means you're excluding specifically 2 and 3, and 2 times 3 is 6. Although, if your brain went there, that's an interesting connection you made. But at least 6 distinct positive divisors, and here's an example. 31, 37, these are consecutive primes. They add up to 68, and that's got 1, 2, 3, 4, 5, 6 factors. Okay. So, the fact that they're primes is probably going to be important. And the fact that they're consecutive primes means that there's no primes in between them. So that's nifty. But, okay. So, let's get the last question out of the way. And, if P and Q are both greater than 3, then P and Q are odd. So it's a sum of odd numbers is what we're talking about. This is even. So 2 is a factor. Okay. So right now, P plus Q looks like 2 times some number, call it K. And this has distinct factors. 1, 2, 2K is definitely different than them. And K, now, you have to ask yourself, could K be 1 or 2? And so, we might say they are distinct, as P and Q being greater than 3 means that P plus Q is greater than 6. So 2K is greater than 6. K is greater than 3. So K is not equal to 1 or 2. And 2K is not equal to 1 or 2. Okay, so I've got 4 factors. I need to find a way to make 2 more. And that's the challenge. Now, I don't think there's anything we can really do about 1 and 2. They're sort of stuck as is. 2K is my whole number, but this K here. If this K were prime, you're stuck. You can't get any more factors. So this K can't be prime. It has to not be prime. And why is that? Well, so we claim K is composite. That is to say, not prime. And why is that? So, K is P plus Q over 2. So the average of P and Q. So, assume P is less than Q, because they did say they were different, right? Consecutive prime numbers, so they got to be different. Then the average sits between 2 numbers, so P is less than K is less than Q. If K were prime, then P and Q would not be consecutive. So that can't be allowed. Therefore, K is not prime. That is to say, K is composite. So we can write K equals A times B with both A and B not equal to 1. Okay, we can break K down into smaller factors. So P plus Q is equal to 2AB, which has factors 1, 2, A, B, AB, 2AB. Now that's 6 factors, but how do we know that A and B aren't the same? And how do we know A isn't 2 or things like that? So let's assume A is less than or equal to B. Because you can. Just pick one of them to be less. Just like over here, I picked P is less than Q. Just whichever one's the smaller one, that's the one we call P. Okay, so we'll assume that A is less than or equal to B. Now, if these are my 6 factors, I need to be able to confidently say that A is not 2 and B is not A and things like that. So, but are they distinct? So obviously 2AB is different from AB. 1 and 2 are different, but how do I know that it's not A and B are also both 2? How come KA can't be 4? Well, K can't be 4 because you'd need 3 and 5 to be your primes, and the primes have to be bigger than 3. So that's at least something to note. So since, what do we have? They are greater than 3, right? Yeah, greater than 3, not greater than or equal. Got to be careful there. Okay. Since P and Q are greater than 3, then 2K, which is equal to P plus Q, and I know I already said this, is greater than 6, so K is greater than 3. So actually that doesn't help me with A, never mind. I was trying to show that A had to be greater than 3, but no, that's not necessarily a thing. So, I think we're going to have to do cases. K is a perfect square. So, I want to get rid of the 2 first. I want to get rid of the 2. So, let's do a case. K is a power of 2. That could conceivably happen in the right situation. I can't think of one off the top of my head, but 13 and 19, for example. 13 plus 19 is 32. Average is 16. 16 is an appropriate power. So actually, what happens there? So, 13 and 19 aren't consecutive, so that's no good. I mean, the principle of what I said is the same, but trying to think of another. 7 and 11 won't work. I think we have to go up pretty. 31 and 33 aren't. 61 and 67. 61 and 67 are both prime, for example. Their average is 64. And that is a power of 2, but you're going to have enough factors. So we claim K. Will it be greater than or equal to 64 specifically? Well, let's see. Could K be 2? No such P and Q exist. Could K be 4? Well, you could have P is 3, Q is 5, but P is then not greater than 3. So could I have 8? Well, you could have P is 7 and Q is 11. Well, no, that doesn't work. So P equals 7, Q equals 11 are consecutive on either side of 8, but have an average of 9. So no, that won't work, that won't work, that won't work. How about 16? Well, you could have P is 13, Q is 17. Those are the two consecutive primes that sandwich 16, but again, the average is not the number you want. The average is 15. 31, well, P would be 32, so P would be 31, Q would be 37, and the average there is 34, so that doesn't work. So, okay, K is at least 64 if it's a power of 2. So 2K is at least 128. And has factors of, well, you could have 1, 2, 3, not 3, 4, 8, 16, I just need one more, 32. So at least 6 factors. Okay, so that's what happens if you're a power of 2. And that means that now when I'm doing this, I can consider at least one of A and B to be different than 2, I guess. But what if A and B were the same? So I did that power of 2 case just on gut instinct, but I don't actually have sort of a grand strategy here, so hold on a second. So 1, 2, AB, AB, and 2AB are distinct unless, well, A and B can't be 1. So unless A equals B or A equals 2. So we need to be able to guarantee that you can do something other than this. So if 2 is less than A is less than B, and AB is equal to K, then we get 6 factors. When can this fail? If K equals 2 times a prime, because then that would mean A is 2, B is P. Or K equals a prime squared. So actually I didn't need to do this power of 2 stuff. Huh. That's a shame. I thought I was being clever. Well, hold on. Do 2 times a prime. Or maybe I did need to do a power of 2 case. K is 8. Hold on. This is trickier than I first thought, this question. And in particular, lining up my casework is going to be a little trickier. So if K is not equal to 2 times a prime, K is not equal to 8, and K is not equal to a prime squared, then we can find A less than B. Oops. if k is not a prime squared, then we can find AB that's equal to k, whose product is equal to k, with A less than B, and that's something that we definitely need. And if k is not equal to 2 times a prime, or k is not equal to 8, we can find A and B with A less than, with A AB equal to K and A greater than 2 less than or equal to B. And those are the two ways this could fail. You could have 2 not be less than A, and or A be less than A be less than or equal to B. I think, have we got everything? Yeah, I think that'll cover it. But let me just run through it again, because you don't want to say, I think that'll do, and then run into a problem later on. Okay, so how can this fail? 2 could be equal to my lowest factor. So for example, the reason I keep including 8 here is because other than the 1, 8, the only other factoring is 2 times 4, which is fine. Your A would be 2, your B would be 4, but your lowest factor would be equal to 2, and that can't happen. Of course, we've already explained, as I was sort of rushing ahead, that k can't be 8. What we want to do is show that k can't be a p squared, or k can't be 2p as well, I think. I think that's where we're going with this. But if k is equal to 8, if k is equal to 2p, then a is 2, b is p, and that'll fail because, again, a is 2. So this last case here is all the situations where any factoring that isn't 1 times the number has a factor of 2 in it. That's the only possibility. Anything else will be a bit more. Right? Other than, well, 16 would be 2 and an 8, which is a problem, or 4 and a 4, which is a problem. So I guess we're learning. And I'm learning where to go with this. So I'm gonna disregard this. So what k have factorings that are only k equal a times b with a equal to b, and k equals ab with a equal to 2. Again, we're assuming a less than or equal to b. So those are the ways things can fail. That if those are the only possible ways to factor things. Okay, so if a equals 2 and b is not prime, then b could be equal to c times d, and then 2cd is different to the factoring ab, but they both still multiply to k, right? like maybe I'm making this harder than it needs to be, but I want to be exact because it is a proof question. It's a proof-based contest. I feel like 8, 16, 2p, and a p squared are the only things I need to worry about. But I've got to be able to show that those are the only things I need to worry about. So if k is equal to p squared, then the only factorings are 1p squared, which we never count, and p. So that's a problem. Okay. If k is equal to 16, then the factorings are 1/16, which again we don't care, 2/8, which would be a problem, 4/4, and that's it. So these are problems. If k is equal to a square with n greater than 4, and not prime, then n is equal to some x times y, with x and y not equal to 1, and so x squared y squared would be a factoring of k. Yeah, I think because it could transpire that it's a fourth power, but if it's a fourth power, x and xy squared will always do because x is not 1. So we can get x and y greater than 1. And since x times y is greater than 4, the geometric mean of them is got to be greater than 2. So 1 of xy is greater than 2. Say x. And then x, xy squared will do. There we go. Okay. So that covers all squares. And that means these situations here, the a equals b's, are done for. So if k is any other square, that's fine. Okay, now what if k is a semi-prime? So what if k is 2 times p or something like that? So any other square was dealt with. So consider k not equal to a square. Then k equals to a times b with a equal b. Can't happen. So we are left with k equal to ab, and no matter what we choose, a equals 1 or 2. Okay? So the two things that could screw up These values not being distinct was if 2 was repeated amongst A or B, or A and B were repeats. Well, we've just made sure that we understand the only times that you'll get repeats, A and B being the same. Okay, that would have to only happen if K were a square. That's the only time you could have something times something be equal to K. That's the definition of a square. Almost all squares are fine. P squared 16 aren't, so we'll have to deal with those cases and show either that they can't happen, like K equals 16, or even if they do, there's something else that we can deal with. Okay? So the K equals P squared, I suspect, will be something we have to work with. Okay? So we don't need to worry about A equals B screwing things up. That'll be handled by those two cases. But what's left? Well, 2 could be repeated. And I understand with K equals 16, 2 is repeated. 2 is... So if K were 16, 2K would be 32, and you'd be looking at 1, 2, and you could either have 4, 4, or you could have 1, 2, 2, 8. But we're crossing that bridge right now. Okay, so no matter how we choose, A equals 1 or 2, then K has only 2 factorings. So I probably should have introduced this a long time, but to count the number of ways to factor a number, and maybe this would have made the question go a little smoother. Let's say M. If I write it in prime factored form, the number of factors are E1 plus 1 times E2 plus 1. That's the number of different factors a number has. Okay? Just a useful thing to be aware of. So if K has only 2 factorings, then K either looks like some prime to the 1 times another prime to the 1. And if 2 is amongst them, you're going to have 2 times some prime. We'll call it R, because I think I was saying, P is already in the question, so let's use R. R squared and R times R prime. Okay. So R to the 1, S to the 1, so K would be 2S, or K is R to the 2 factorings, therefore 4 factors, is what I forgot to say. Or it could be R to the 3. And since 2 is a possibility, K would be equal to 8. Oh, this is so much clearer now. Oh, I'm so much happier. So either you get A equals B, and that would mean you are a square, or no matter how you factor, you get one of those factors has to be 1 or 2, and that leads to 2 times a prime, or 8. So those really were all the cases. So cases to check. First of all, I've already noted K can't be 8. It's impossible. P would have to be 7, Q would have to be 11, and their average is not 8. Same way, K can't be 16. The 2 consecutive primes around 16 are 13, 17, and their average is 15, not 16. So those 2 cases can't happen. Here we go. So what if K is R squared, R is prime? Then P plus Q, because it's been so long since I said P plus Q. So I've been worrying about my cases, because if I don't have my cases lined up right, somebody marking this is going to say, they forgot the something to the power 5 case, or something like that. And I'll lose marks. So I have to make sure my cases are in order. And even setting those up is sometimes worth marks. So, I don't regret the time that I spent with that. I regret that it did take so long. So P plus Q, and so we're looking at 2R squared. But this has factors 1, 2, R squared, 2R squared, so, Oh, and incidentally, r has to be greater than 2, since k can't be equal to 4, because then p would be equal to 3. But that's only 5 factors, so what's going on here? Oh, 2r, 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 2r. There we go. Because it's 2 to the 1, r squared, and that would have 6 factors. So it has 6 factors, so we're happy. So even though that looked like it could have caused problems, it doesn't. And now, what if k is just equal to 2 times some r? Then p and r is prime. And I'm going to assume r greater than 2. So p plus q is 2k, so that's going to be 4 times r. And that has 6 factors. 1, 2, 4, r. Although r could be less than 4, but it doesn't matter. Not r squared, 2r again, and then 4r. So that one's happy as well, and these other 2 cases just can't happen. Great. So that, I think, works it all out. Now, I realized sort of late in the game that I probably could have used this prime factoring thing. And so I wonder, is there... So the question's over, but I'm wondering, is there a cleaner way to do this? So p plus k, let's say it like this. So suppose p plus q is equal to 2k, which is equal to 2 to some power, and then another prime. I realized I was using p1s. I'm gonna, to avoid confusion, use r's. So r2, e2, and then rm to em. Suppose that has less than 6 factors. And then E0 is at least 1. So if we have less than 6 factors, then we have P plus Q looks like either 2... Yeah, I think this is probably going to be a lot easier. 2 to the... I don't know, let's say E, where E is less than or equal to 4, or P plus Q is equal to 2 to the E R to the F, where E plus 1 times F plus 1 is less than or equal to 5. And so, as a consequence, I mean, product of 2 numbers, both greater than 1, that would really have to be 2 and 2, or 1 and... well, no, it can't be 1 and 3, because they're at least 2, so it'd have to be 2 and 2. And so P plus Q would have to be 2 times R. And that would mean that P is less than R is less than Q, which we sort of already talked about. You can't have a prime in there. Or you could have... oh, you can't have 3, can you? So you had R there, and then F, S to the G. You'd have E plus 1 times F plus 1. And this is going to have to be greater than or equal to 8 because E, F, and G are greater than or equal to 1. But that needs to somehow be less than or equal to 5? I don't think so. Just keep my writings the same. So that can't ever happen. So really the only possibilities were P plus Q is a power of 2, or P plus Q is 2 times a prime, both of which can't happen. Oh, this question was so much easier than I was making it. Darn it. Ah. Well, that makes me, I guess, a little sad, because I don't like when I don't come up with the best solutions. It's a feeling I've had many times talking with people after contests, and they're like, oh, how'd you do question 7? And I said, I did it this. And they said, really? You could have just done modulo 19. As if somebody's going to think of modulo 19. But if only I'd realized to use the unique prime factorization earlier. Oh well. What can you do? You can't really do anything. If it's after the fact, you can just say, wow, okay, I'll remember that, I'll learn it, I'll try. Next time somebody's talking about factors, I'll try and think of that faster. But in the midst of a contest, you do not want to say, oh, there probably could have been an easier way. You want to move on to something else. Only if you have time at the end and are reviewing should you try and make your solutions simpler, more efficient, more elegant, because sometimes that can factor in when you get marks. But during the contest, never, ever, ever say, I just finished question 9. I wonder if I could take out a paragraph or 2 of text. No. Get question 10 done before you go back and start trying to revise things. Only when you realize the rest of the contest is a lost cause based on time or your own ability should you go back and revise already completed solutions. But, darn, I'm disappointed in myself. Anyway, up next will be, it is question 10, right? We were on question 9, so up next will be question number 10. I will see you for that in the next video. Thanks for watching.